Hello everyone, I hope you can hear me. This will be lecture 7 of probability and statistics. So we will continue with where we left last time. We were discussing the prisoner problem, and then we will digress a bit, go to a related problem in game theory, and then we will see some random walks. And after that, we will also see some examples for conditional probability. So let us recall what we did last time. This was the problem. Long ago, a prisoner was to be executed. In response to his supplications, he was promised that he would be released if he drew a white ball from one of the two similar urns. The provisions were that he had to distribute 50 white and 50 black balls between the two urns in any way he liked. Okay. After which he had to draw a ball at random from one of these urns. The question is, how should the prisoner put the balls such that the probability of his release is maximized? So this is the problem we were discussing last time. And so just to recall what we were doing last time. So he had two urns, right? So urn 1 and urn 2. Okay, and he had to distribute the balls, and here also he's distributing the balls. Okay, so it could be a mix of white and black balls. Here also he has white and black balls. So the idea here is the freedom he has is that he can distribute the balls in any ways he likes, but after that the urns, he doesn't know which urn is where and where did he put more white balls and so on. He will be blindfolded, and then he will be given a choice to pick, and if it turns out that he picks a white ball, then he will be released. So that was the problem. And in the last class we saw that if we put only white balls in one of the urns, so if he puts all white balls, and in the other urn this is where he puts all the black balls. So in this case his probability is, so there is a half to choose this, half to choose this, and then furthermore he has probabilities when he goes inside. So in this case it's let us say if he goes to urn 1, so probability of picking that is half, and there after that once he chooses that, since he has all white, it's 1, and then similarly if he goes in the other way, so half, but then here there is no white balls here, so the probability of choosing white ball here is, so in total here he got half. Okay, so another possibility is when so these are the two cases I discussed. So let us say another possibility is that he puts 25 white plus 25 black here, and then here he puts 25 white plus 25 black here also. So in this case it's half to choose the first urn, and furthermore to choose white out of these equal number of white and black, so it's 25 by 50. And similarly here it's the same case here, so 25 by 50, so which turns out to be again half, which is same as this half. So we were asking whether we could do this in a different way. So what we can do here, right? So so the prisoner is allowed to put any number of white or black in any of them. Okay, so let us see the solution to this. Yeah, so question is, how did the prisoner arrange to make his chance of success as great as possible what happens if he puts equal number of whites and black ball into boxes? This is something we already checked. So the probability of choosing white ball is half, and so can he do better? What if he puts all white in one and all black in the other urn? So this also we have described, and this is again half. Can he still do better? If yes, how? So, well, what he can do is the following: put 1 white and 0 black in urn 1. So he puts 1 white. Okay, so 1 white and then 0 black, and here he puts 49 white and then 100 blacks. Okay, so let us calculate the probability of his success. So probability of okay, this is the way we define the success. Okay, so the probability to choose the urn 1 is half, and once he goes there is only white, so choosing white is this, and then probability to choose the urn 2 is half, and inside there probability to choose white is 49 divided by, okay, I'm sorry, this is not 100 here, but this is 50 black, right? There are only 50 blacks. Okay, so so this is 49. Choosing 1 white here in the urn 2 is 49 number of favorable cases divided by the total number of cases, which is 99. Okay, so you will see that this is half plus this is again like you can approximate that to be a half. Okay, approximately it's like a, you can say that it's like a half, so it's like approximate here. Okay, very close to half. So this turns out to be half plus 1/4, right? So you take 4, so it's like 3/4. So 3/4 is indeed much better than his success that were there in the trivial cases. So he can increase his success by doing a distribution like this. Okay, so this is one of the cases where you encounter the tree is like tilted more towards, so it's like just this, but here the tree is more, I mean, the more balls are here and so on. So this is not really like distribution and so on. What it tries to tell us that distributions can change our probability, obviously. Okay, so we will look into more in detail. Okay, we will have a lot of lectures on distributions. Okay, but this is what he can do to maximize. This is the maximal he can get. You can see that there is no other way he can increase his chance more than this. Okay, so this was the problem that we were discussing last time. Okay, so a subsequent question is, what is the chance of success if the prisoner had been allowed to distribute 100 balls among 4 urns? Okay, so what if the problem is changed to 100 balls and the number of urns is changed to 4 urns? Okay, so I leave this up to you as an exercise, and this will be discussed in the tutorial. You can like immediately see, because there is a continuation from the previous argument. And what if the number of balls is drastically increased? So let us say you still have 2 urns and urn 2. So what if the number of balls is increased, right? So is the probability increasing or not? Okay, the probability of success increasing or not? So these are simple corollaries of what we did in the previous slide. So I let you explore. It should be fun to explore on your own. Okay, there is a related problem in game theory. It's called prisoner's problem. So it has a different it's a different problem actually. So there are like 2 prisoners, let us say Fred and Wanda. Right now it's not related to probability. Okay, it's more towards game theory. So let us say there are 2 prisoners, Fred and Wanda. If both of them and they are like accused, let us say. Okay, they are not really they are not yet proven to be guilty. For the moment, they are accused of some crime, and if both of them do not confess their crime, then the police will give them a term of 2 years to serve in the jail. If they confess to crime, then the partner doesn't. So let us say Fred confesses to the crime, but Wanda doesn't confess. In this case, the partner not confessing, okay, will serve 10 years. So let us say Fred confessed the crime and Wanda don't confess, then she will serve 10 years now. Okay, so she will have a harsh punishment of 10 years. And the other way also, if Wanda confesses and Fred doesn't, then Fred will serve 10 years and Wanda will be released. Okay. If both confesses, then both end up spending 5 years in jail. Okay. So these are the conditions you have seen. So these, so if both of them do not confess, okay, then they serve 2 years. If one confesses and other not, then 10 years. If both confesses, then 5 years each in jail. Given that Wanda and Fred have no reasons to trust, okay, so assuming that Wanda and Fred have no communication between them, they may not trust each other at all. So what are the good options for them to minimize the term in the jail? So this is the table that we can make. So for Wanda and Fred. So if both don't confess, then 2 years each. If one confesses and the other don't confess, then 10 years. Similarly for the other way around. Okay, and then if they both don't confess, then 5 years each, right? So this is these are problems. It's part of something called two-player game where the players are trying to optimize their profit in some sense. Okay, so some of the applications of this type of problems is called cooperative games, is in even in business, right? So you may have seen why people keep usually why people keep let us say same type of shops nearby. Okay, so there is some kind of a game theory involved there. So why it is actually beneficial when you have similar type of let us say electronic shops nearby rather than having them very far apart. Okay, so I will give some link to some blogs there. Okay, so indeed, if both, hello. Yeah, please turn off your microphone. Hello, please turn off your microphone and you can talk, but I can't give you a control of the presentation. Okay, I can't give you control of the presentation. That's not allowed for you during the class. So you cannot ask me for a control. But what I can, but what you can do is you can talk to me. Okay. Okay. So let us continue. If there is anything, any question, any doubt, then please let me know. Okay. Okay. So okay, I continue. So I don't know why some of you keep asking for control of the presentation. I don't know why. You can always talk. I don't know what is and why don't you turn off your microphones? All this is going into the recording, like all the distractions that you are doing is going into the recording. Last time some of you were playing some songs and that got recorded. Okay, whatever, I will send these videos to the dean and they will look into this. Anyway, I will continue. So let us say indeed if both of them don't confess, okay, so let us say if both of them don't confess, then it is the best for them. Okay, so if they don't confess, then it is the best for them. It's like 2-2. Okay, so that's like the minimum term that they can hope for together. Okay, but the point is like they are greedy, so they will think of getting away with 0 term. Like even 2 years in jail is like not really a good idea. So they may not trust each other, right? So in that case, it's like But the other best option is that when they both confess, because in the other cases, one of them has to spend 10 years in jail. Okay, so in this type of cooperative games, you want both the sides to benefit to some extent. Like you don't want one guy to suffer a lot and the other guy not at all. Okay, so a optimal strategy, another optimal strategy would be if they don't confess. Okay, so in this case it's like 5-5. Okay, so there is a big theory behind this. This is a very simple example here, and one can go into wide variety of problems, generalize the problem, and so on. I just wanted to digress a little bit because there is a similar, because it's a prisoner's dilemma problem. It's a slightly different problem, and of course, game theory can be probability can also the problem can be posed as a probability problem as well. Okay, by doing some variations. Okay, so I hope you can go and look into this. So these are the cases where both can benefit. Okay, so-called Nash equilibrium you can think of. So this is due to John Nash, and there was a movie made on him. So I can ask you to go and look into this. He's one of the most well-known mathematicians of modern times. He has solved very difficult problems ranging from differential geometry, partial differential equations, game theory, and you name it. And these were very, very difficult problems. Okay, so this guy is really, really good. Okay. In the movie, he talks about how he came up with this this idea of Nash equilibrium and so on. So you can go and watch this. Okay. So, and some of these can be found in the topics in applied optimization course that I teach. Okay, so it's part of optimization problem you can think of. It's a part of a min max problem, min max, and then you have some objective over x, y, and you minimize and maximize over y. So solution to this is often yeah, you have to find the, it's not just maximizing one guy, minimizing one guy, but it's a simultaneous thing. So you have to satisfy both the agents x and y here. Okay, so it's optimization problem, and such type of problem can be formulated as a two-player game. Okay. Okay, so I leave this up to you. Now we come back to applications of probability. So here I have a short video on random walks. Okay, so random walks, Brownian motion, and so on. So let us have a look into these videos. Okay. So here I have, and okay. Okay, we have to shift. Okay, I don't know why now it is not playing. This is the problem with videos. Okay. It is not.
Sir. Sir.
Hello?
Sir, no, it's not audible to us.
Which one? What is not audible?
That's playing.
Okay,
We
video.
can't.
Okay, so it's fine if it's not audible. You just watch this, because Yeah, it may have to do with the mic that is not able to capture. I don't know, but here audio won't matter much. Okay, so I would say just watch. What matters here is the Brownian motion, that the picture that is going to tell you. Okay, so yeah. Okay, so you may have seen the picture, but this was one of the oldest one where they did this in black and white. But I have a more clear one. So let us say let us watch this. So I can do the commentary on this because you cannot you don't hear this. Okay, so this is so-called Brownian motion. It's one example of a random walk in nature you can think of. So you can imagine these particles to be, let us say, some nanoparticles like pollen grains, very fine. Not just the original pollen grain; they are still very big. You have to burst them into very small nanoparticles, and then you throw them into water, and then this is how they interact with the water molecules. And so the modeling here is more of a random walk, like the which direction they will go. It's more random here. Okay. So after some, so although it's random, and like you cannot really predict where this particle will go. Okay, but after some time, if you observe, then there have been, on average, there have been some movement to some place that you would not have expected. Okay, so this is so-called Brownian motion example, and in probability models, it can be modeled as some kind of a random walk. We may not know random walk yet, but we can start with some simple random walks. Okay, so we can go to the simplest random walk, and the simplest random walk is this, where let us assume that there is some person, okay, who is standing at so let us say there is some person who is standing here at position 0, and let us say the guy is drunk, so you can go either right or either left. Okay, and you don't know like which direction he will go. There is some probability to go to the right, and there is some probability to go to the left. Okay, at 0 he is at 0 with probability 1, and after that we can define probability that he will go to the right is q, and hence the probability that he will go to the left will be 1 minus q, because the sum, he will go in either direction anyway. He is supposed to go in either direction anyway. He will not stay there at 0 all the time, right? So so this is how you can assign. In the simplest random walk, we can set q to be half. Then the probability that he will go to the right is half, and probability that he will go to the left is half. Okay. So consider the person at x equals to 0. He can travel one step to the right or to the left. So he can travel only one step at a time. Okay, so he travels one step to the right with probability q, and hence to the left he will travel with probability 1 minus q. We can define a simple random walk. A simple random walk. Yeah. A simple random walk in 1D is defined as follows. A walk in a simple random walk is called a simple random walk in 1D if there is an equal probability of either going to the right or going to the left. Okay, so if we set p equals to well, I did not define p here. Let us say p was to the left. Okay, so if p equals to q equals to half, then we call this a simple random walk. We could have defined the biased random walk. So in general, if q is not half, then we can call it biased random walk. This is how we define it. Okay. So what is the probability that the person after the ith step will be at x equals to 0? So these are the questions we can ask. Okay. If you recall this problem, although it looks like a very different problem, but these are the problems we have actually done already before. So there is no, it's just a model is different here. That's the only thing. So sometimes we have to think about that. Okay, so let us do some analysis of this simple random walk. Okay, so what we can do the analysis using the choice tree that we have seen before. So earlier we saw choice trees on the boxes and so on. Okay, so we had 2 balls and then we had 4 balls and so on, and then we built, and then we saw what are the probabilities of picking these balls and so on. And then choice tree we also saw in the Galton board experiment, where we were throwing the marbles from the top and we were observing how they were distributing at the bottom of the Galton board. Okay, and then there also we saw the probability. So choice tree really helps, and I'm stressing this several times now. So again, we can build the choice tree. So let us say he starts at position 0. Okay, so this is the position 0 he starts with, and the probability here that he starts from 0, he is at 0 is 1 here, and then he takes some moves to the right or to the left. And in a simple random walk, he can choose each branch by half and half. Okay, so this is what he can choose, and then here he can arrive at let us say we give the label as -1, -2, -3, and this is +1, +2, +3, and so on, right? So this -1, this +1. And similarly, these guys now. Okay, so from -1 now he can go to -2, or he can go to 0. Okay, or here from +1 he can actually go to 0, and then he can go to +2, and so on, right? So the probability that he will be at some place, let us say +4 and so on. Now you can calculate from here, right? So this is like -2 is like -3, and then -2 + 1 is like -1 here. Okay, and then similar 0 -1 it goes here, and then here is +1, and so on, right? So you can see that although this is a random walk problem, simple walk, but the tree that we are trying to build, the decision tree here, is looking very similar to the Galton board example that we saw before. So from here again, to recall, if we go ahead and compute the probabilities will again be the same, right? Because it's very similar to the Galton board experiment. Okay, because we have like half here, right? So again we have so again we have like half times half here. Okay, so this is the same thing here actually. Okay, so half times half, and then plus another half times half here. Okay, so it's like 2/4 for this guy, and so on, right? So again here, to answer a problem like this, you can build choice trees very quickly, and then you can use the so-called Pascal's triangle and so on. And again, for any node that someone tells you, right? So any node that someone tells you after how many steps, right? So this is like after the first step he took, after the second step he took, after the third step he took. And in the third step, what is the probability of lying in one of those nodes, like -3, -1. Okay, and then 0 will be one case here. Okay, and yeah, so all these points that you are lying in. So after third step, and what is the probability that you lie in one of these? Okay, so these are the questions you can answer, and this again follows from the Pascal's triangle. That's why Pascal's triangle is like interesting in the sense that I know the probability of reaching here, right? So this is n choose k, and then where and then I divide by 2 to the so this is like the level number, right? So this is like level. So here I divide by the by the level, right? So here it's n, right? So I divide by that, and this is how I know the probability of where I am. So someone can ask you any arbitrary place, what is the probability that you will be here after n steps and so on, right? So this is how you can answer this again. So my motivation for this was that many things are indeed related. Now you can also do this analysis for the biased case where you have something like this, where q is not necessarily half. Okay, so you can build the tree like this, but now you have to do some extra housekeeping here, because let us say probability to go here is q, and this is 1 minus q. So then you have to make sure that you keep this in mind. Okay, so probability to go to the right is q, and probability to go to the left is 1 minus q. Okay, so probability that that he will hit this is 1 minus q. Okay, and then if he goes in the left again, so it's again 1 minus q. Okay, so this is what you have to multiply now. Okay, so probability that he will hit here is 1 minus q squared. But if instead he chooses to go here, okay, then you have this case, right? So you have this case where you are going like this. Okay, so this is like a 1 minus q. Okay, so it's like 1 minus q, but then there will be something also from this side. Okay, so this is like q, and then this branch is 1 minus q. Okay, plus 1 minus q. Okay, so you have to add up these probabilities here again, and then so this is how you can do. And I would request you to find a general formula for this. In the case of the simple case, we had 1 by 2 to the n. Now I want you to generalize this to the case where we have q to go. So what you can expect is something like this. Okay, and so on. Okay, so you verify this. Okay, verify that for the biased case you will have something like this. I'm not completely sure unless I derive this, but you will have something similar. So I would request you to verify this, and you may discuss further details about this in the class.
Excuse me, sir.
Yes.
Sir, what was in last question?
What was?
N and K in the formula.
Yeah, so you remember the Pascal's triangle? From the Pascal's triangle, you can what were n and k in the Pascal's triangle? When we draw a Pascal's triangle, what were the n and k? How did we derive? How did we come up with n and k in the Pascal's triangle? What was n and k there?
And with the total number of balls or the objects we are considering.
Yeah. Right. So another way to recall Pascal's triangle is via the grid, right? So and then you can make this into a tree, obviously. Okay. So if you forget that, then a good way is like this. So what we are asking for is how many ways I can reach to this, right? So the tree view is like this. Okay. So I'm just doing this so that you see the levels here. So this is how the tree is progressing, right? So what we are asking for is the probability. So what is the chance that I will reach this node, right? So this node is what? Okay, so in this case 1, 2, 3 and 3, 2, right? This is 3, 2. Okay. So what we are asking for is what are the ways for me to reach this 3, 2 here, right? So what are the ways for me to reach here? Okay, this keeps and then so what are the ways for me to reach here? So how do we calculate that, right?
Okay.
So that's so these nodes correspond to the ones in the tree here, right? Okay. Now we can do random walk in 2D. So let us say we have a 2D problem, but we are doing random walk, but this is slightly more complicated than 1D problem. So in 2D, let us say you start from here. Okay, let us say there is Alice that starts at point A and then walks one edge right or up. So Alice can walk one step right or she can walk one step up. If she is here, then she can go like this or she can go like this. There are only two steps, two things here, right? Right or up. Okay. And okay. Okay, at the same time, Bob starts at point B. So Bob starts at point B and he walks one as left or down. So he can go like this, one step left, or he can go down. Okay, so he can go down. So if Bob is here, then he can go left or he can go down. Okay, at each step, Bob can go left or down, and each step Alice can go up or right. Okay, these are the moves that are given. So the question is, what is the probability that Alice and Bob meet during their random walks? So what is the probability that they will meet during their random walks? Remember that there is also a probability that they will never meet. Okay, so there are cases where they will never meet, right? So obviously, like if Alice goes like this, and let us say if Bob goes like this. Okay, so it is not just about crossing the path. Okay, you should understand the problem here. It's about meeting at the same point at the same time. Okay, meeting at the same point at the same time. So it's not, the problem is not saying that they cross the path. So for example, one way they could have crossed the path is like this. If Bob goes like this and then he goes like this, so they cross the path here, but that did not meet, they did not meet at the same time. Okay, so the question is when they will meet at the same point at the same time, and what is the probability of that happening. Okay, so this is the problem. So this is a slightly tricky problem. First of all, yeah, so this is the experiment, you understand. So experiment here is that two persons are walking from two corners of a random grid. Okay, and then you have to identify what is the proper sample space you are talking about, right? Are there redundant moves that really doesn't make any sense in the sample space? Okay, and what is the event here? So event is that both A and B meet at the same point at the same time. Okay, so you have to figure out all these things in problems like this. Okay, so you have to figure out all this in problem like this. So let us think about this, how we can do this. Like the first question you should ask is, what are the cases where they meet at the same place at the same time, right? So I can ask you a question. I can ask you a question like this: can they meet here at the same place at the same time? Is it possible that they can meet at this point at the same time? So can they meet this point at the same time, right? So you should ask what is the time that will be required by A to reach here, right? So what is the time required by A to reach here? If A has to reach here, Alice has to reach here, she must have to follow some number of steps. So let us say one possibility is this: 1, 2, 3, 4, 5, 6. Anyway, she goes here, she have to follow 6 steps, right? So 1, okay, 2, 3, 4, 5, 6, or she can go 1, 2, 3, 4, 5. Okay, sorry, 6. Okay, so total is 6. So Alice, if she comes here, then Alice will need 6 steps for Alice. Now let us look at the Bob, right? So Bob, if he wants to come here, so he can go down and left. So let's say 1, 2, 3, 4. So to reach here, Bob will take 4 steps. Okay. So this is a case where they cannot meet. Okay, they cannot meet at this point because this is the point where they cannot meet at after the same number of steps. Okay, same number of steps because they are starting simultaneously, right? So if they meet, they have to meet at the same number of steps, but that will not happen because Alice will take 6 steps and Bob has taken 4 steps. That cannot happen if they walk simultaneously each time. So this is ruled out. So they cannot meet at this place at the same time. So the first thing you should think about is where they can meet. Okay, if there are points on a grid where they can meet at the same time, what are those points? Right. So you can tell answer if you want to. Okay. Okay, so I see the answer here, which is like it's saying it's diagonal. It's a diagonal. It's like anti-diagonal or the usual diagonal. Can it be the usual diagonal? Like there are 2 diagonals here, right? So one diagonal is like this diagonal, and another diagonal is like this diagonal, right? So which of the diagonal you are talking about? Okay, anti. Okay, that's correct. So Sarthak is replying, and Pavani is replying. Mehul replied. Vinal replied. Yeah. Okay, you are right. So it is like anti-diagonal. Okay. So this is like the anti-diagonal case. We are right. So that's our first job is done in the sense that we have identified the points where they can meet. Right. So these are the points they can meet, right? So these are the anti-diagonal grid points they can meet. Okay, so now what are these grid points, right? So these grid points, we can number these grid points, right? So this is like 1 and then 4, right? So this was like the grid point 1, 4. Okay. So and what are the number of ways they can hit this diagonal? That is the second step for us, because now we have identified where they will meet. That's fine, but then we are asking now in how many ways each can reach there, right? So if this is the point here, then from the Pascal's triangle we know that this is going to be just only one way they can reach. Okay, because Alice is allowed only up or right move. So if C is going to reach here, she has to take only up move, and then she will reach here. Okay, and if Alice has to reach at the this case, we have already done this now many times. So if she has to go there, then these are the 5 ways she can go, right? So you can check. Like this, 2, 3, 4, and then 5 ways, right? And this is also coming from the Pascal's triangle. I add this 1 and 4, and then I get the 5, and then I add this 4 and 6, and then I get the 10. So you see, Pascal triangle again is helping you, especially if you are doing this grid type problems. Then Pascal triangle can help you a lot. Okay. So let us clear things up here. Okay. Okay. So what we know is that Alice can reach diagonal point this in 1 way. Alice can reach this diagonal point in 5 ways. She can reach this diagonal point in 10 ways, 5 ways, and 1 ways. Okay, this due to the symmetry of the problem, For Bob also it's like the same case, 1 way, 5 way, 10 way, 10 way and 5 way and 1 way. Okay. So what we have identified are the number of ways they can reach this antidiagonal, but the problem is like they may not, because Alice might reach this node, but Bob might reach this node. So there is still, because they are working randomly, right? So this is a random work problem. So there is no guarantee that they will. There is no guarantee that they will come at the one node precisely, because they have no coordination among them. So Bob may be here, Alice may be here, although they have taken the same steps, because they are reaching the antidiagonal. So they will take the same number of steps, but they are not meeting. So they will cross each other and they will never meet again after that, because they are not allowed to go back anyway. So they will never meet again once they cross the antidiagonal from either way, unless they meet. So yeah, so sample space now you can figure out. So the sample space would be how much, right? So you have to count the number of ways Alice can reach the antidiagonal. Okay, so all these antidiagonal, and the number of ways Bob can reach these antidiagonal. To reach the antidiagonal, they have to take exactly 5 steps. Okay, so if they can meet only at the blue circles, which is after they have taken the 5 steps. So one thing we are sure about is that according to our problem requirement, which is about meeting, it's only when they take 5 steps. And now the question is like how many ways they can take these 5 steps. Okay, so how many ways Bob can take 5 steps, how many ways Alice can take 5 steps. Okay, so now things are more or less clear in our head. So number of ways they could have taken 5 steps is 2 to the 5 each, right? So Bob can take 5 steps because there are 1, 2, 3, 4, 5, right? So Alice is allowed to go up, or so the sets up or right. Okay, so this is for Bob, and for Alice it's down and left. So there are 2 choices. So it's like 2, 2, 2, 2, 2. This is for Alice, this 2 to the 5, and same thing goes for the Bob, 2, 2, 2, 2, 2, and this is again 2 to the 5. But since 2 ways are involved, we have to multiply, because we are asking about number of ways among 2 items. Okay, so by the product rule, we have 2 to the 5 times 2 to the 5, which is 4 to the 5. Okay, and this comes out to be 1024 total number of paths with 5 steps. Okay, now the number of ways Bob can reach the blue dots is given by binomial coefficients or Pascal's triangle. This is something we have already noted. So this is again a Pascal's triangle that is helping us realize the number of ways they can hit this diagonal, right? And same for Alice from the other way around. So the total ways Bob and Alice could meet at the blue dots is like square of the polynomial. So let us fix some dot. Let us say this is 5, right? So number of ways Alice can reach to the 5 to this antidiagonal is like 5. And let us assume that Bob also is reaching the same antidiagonal. So Bob also it's 5. By product rule, it's 5 by 5 square. That's one case. Now let us fix this blue dot, and a number of ways Alice can reach here is 10. Number of ways Bob can reach, assuming that they do reach at the same point, it's 10. The total number is 10 square. Now the question is, in one, because they can meet in any of the ways, right? So they can meet in any of the ways. So then, because any case is okay. So here comes the sum rule. Okay, so sum rule not just among 2 items, but now we have like 1 item, 2 item, 3 item, 4 item, 5 item, 6 items, right? So we have to sum over this they don't intersect obviously because they are in a different, they give you different paths. So then we have to apply the sum rule also, right? So number of ways 1 square times 1 square, and then this is 5 square times 5 square, this is 10 square times 10 square, this is 10 square times 10 square, this is 5 square times 5 square, and this is 1 square times 1 square, and any of the interdiagonal is okay for us. Remember sum rule, any of the object is okay for us, type A or type B, then we sum over this. So then we will sum over this. So then sum rule is also coming into picture. So this is how they will be meeting, right? So these are the ways they can meet. Okay, these are the ways they can meet, and this is like 252. Okay, so these are the ways they can meet 252, and the number of ways they could have taken 5 steps is 2 to the 5. Okay, so number of ways they can take 5 steps 2 to the 5, which is 1024. So 1024 is there. So the original problem was just any random walk, but then when the question asked you when they can meet, so you reduced your sample space to the cases where they are only taking the 5 steps. Okay, and so the valid sample space here became 1024, and the number of favorable cases out of these became 252 here. Okay, because that's the places where they can meet. So this is how you have to model sometimes problems like this to identify sample space and favorable outcomes in a correct way. So if we calculate this, then this will turn out to be 24 point. The probability that they will hit at some point is this. Now I can generalize this question, and that can go into the tutorial. Is do this for n by n grid. Okay, so n by n grid. So generalize this problem. So this will be discussed in the tutorial from tomorrow. In tomorrow tutorials, they will discuss this to a general case. Okay. Now I would like to move to something called conditional probability. So far what we have done is probability. I mean, of course, everything is probability here, but what we have done is like simple calculations of probability without any prior condition given to us. So before telling too much, let me introduce some examples where you can see what is the meaning of conditional probability. So let us consider an experiment where we throw two dice A and B simultaneously. Okay, and odd number, the event is odd number on the first die, and the question is what is the probability of the event. Okay, so we have two die. Okay, and we throw these two die simultaneously. Okay, the simultaneous case. Event is odd number on the first die. So event, as we know, is a set, and since there are two die, the output will be a pair. So and what we are talking about is odd number on the first die. So the possibilities are 1 1, okay, 1 2, 1 3, okay, 1 4, and 1 5, and 1 6. Okay. And similarly you have odd number on the first die, so it's like 3 1, because you don't care about the second one, so you have to list all of them: 3 1, 3 2, 3 3, and 3 6, and then last one is 5 1, 5 2, and 5 6. Okay, so the event cardinality of the event is how much, right? So for the first odd one, you had 6. For the second odd 3, we had 6. And for the third odd starting with 5, you had 6. Okay, so you had 18 here. And then what was there in the sample space? Sample space is like 6 times 6, so it's 36. Okay, so order of the sample space. So the probability of the event is nothing but cardinality of the event, cardinality of the sample space. Okay, so this is like 18 by 36, okay, which is half. So that's the answer here. Okay, so probability of this event is half. Okay, so let us now Now let me remove this. Okay, so now let us consider this problem now. The event is the same, but now you are given some condition, additional condition, that die B will always show even. Okay, so die B is made in such a way that that it will always, like someone told you that die B is will die B is going to show you even. So what is, so the additional condition is given to you that die B output will be even. Okay, so this is what we mean by conditional probability, where some condition is already given on one here. Okay, so for the die B, I already am given that that when I throw die B is going to be even. Okay, so in that case the sample space will change here. Okay, because these cases are going to be removed. Okay, so these cases are going to be removed, and this is something I have been told by someone, that that die B is even now. Then now what is the probability that that you get an odd number on the first die? So I will remove this because of the given condition that someone told me that die B actually has produced even. Okay, or is going to produce even. So these things go out. Okay, so these things go out. Okay, so these things go out, and so on. So you will see that in this case, given that the die B is even, okay, now the probability of the event E, given that die B shows even, okay, someone told me, okay, then in that case E will change, and hence the probability will change. Okay, hence the probability is going to change here. So this is this is so-called conditional probability. So we will okay, we will look into this. Okay, I don't know what is the time now, because it's like 10:30. Okay, it seems like we are we have done we are done with the class, I guess, right? We started at 9:30 and we are supposed to end at 10:30. So I believe we can stop here, right? Because it's like 10:30 already, and we can continue in the next class. Okay. Okay. Thanks for your attention, and then I can stop now.
Sir?
Yes.
I just wanted to ask, is there any changes with the tutorial for the